Eliezer Yudkowsky's recent comments and doomerist posture towards artificial general intelligence have triggered a lot of discourse. While much ink has already been spilled on the subject, I think it's important to dig into some of the principles underlying his ideas and why people disagree. My guest today, Scott Aaronson, is the chair of computer science at the University of Texas at Austin and director of its Quantum Information Center. Our discussion starts with his perspectives about the state of quantum machine learning and its limitations. We then discuss his recent work at OpenAI, where he has been researching the theoretical foundations of AI safety and developed a watermarking scheme for identifying AI-written text. His comments on the orthogonality thesis, that an arbitrarily intelligent being could have arbitrarily stupid goals, are worth reflecting on. I hope you'll take as much away as I did from his perspectives. This is the Gradient Podcast, and I am your host, Daniel Bashir. As always, if you aren't already subscribed to The Gradient, go ahead and follow us wherever you're listening to this podcast. You can also follow us on Substack, where you'll get notifications whenever we release a new podcast episode, article, or newsletter. But now, without further ado, Scott Aaronson. Professor Aaronson, you've recently been doing some very interesting work with OpenAI, but your background is as a quantum computing researcher. So I do have to ask where and how you started thinking about AI in the first place, and then perhaps eventually, how did you come to start working with OpenAI?
Yeah, so I've been curious about AI for, as long as I can remember. Actually, when I was an undergrad at Cornell, I worked on the RoboCup team, doing AI for the, soccer playing robots. That was a key experience for me that convinced me to not become a software engineer. Because I realized that while I love programming, making my code work with everyone else's code and getting it done by a deadline and documenting it and so forth, that I kind of stunk at those things. Then I went to grad school for a PhD in CS at Berkeley. And it was actually the AI and machine learning people who recruited me there. And I spent a year doing that. And I sort of, I had this secret love of quantum computing. But I wasn't sure that I could actually do anything new in quantum computing. And this was back in, the year 2000, but I had a dream of somehow combining AI with quantum computing. Looking at the quantum versions of all these ML concepts like graphical models and Bayesian inference, and I never managed to get very far with that. And then I just after my first summer after my first year at Berkeley, managed to solve a big open problem in quantum computing, and then I was kind of pulled into that, And then I did quantum computing for mostly for the past 20 years. Now around 2010 or so, I learned something that if I had just had a little bit more self-confidence, it turns out that you don't really need to say anything interesting about quantum AI in order for thousands of people to get super excited about it. Right. So, quantum AI sort of became a whole field, right? I would say, around 15 years ago, something like that. Okay. And, people became, extremely interested in, how much can quantum computers speed up, the central problems of AI, whether that means search, optimization, training, deep neural networks, inference, any of these things. And, I think those are indeed enormous questions, right? That's, like I would say, a large part of the question of, how useful will a quantum computer be, is tied up with how useful will it be for those tasks. But we're up against kind of a fundamental difficulty that goes all the way back to the beginning of quantum algorithms, say 30 years ago, which is that if you want an exponential speed up from a quantum computer, it seems to be only for very specialized problems that we can get that, right? And to explain why would require going into some of the details of what a quantum computer is and how does it work. But the two really huge examples where we're pretty confident that a quantum computer could give us an exponential speed up are, first of all, just simulating quantum mechanics itself, right? Which was the original application that Richard Feynman had in mind 40 years ago when he proposed the idea of quantum computers. And second of all, breaking public key cryptography that currently protects the internet, right? Which is the famous thing that was discovered by Peter Shor in 1994, that a quantum computer just so happens to have the right properties to break, the crypto systems that we just so happen to use right now, which tend to be based on problems in number theory, like factoring huge integers or discrete logarithms, things like that. Now, what people usually want to do in AI falls into neither of those two categories. You're given some arbitrary system of constraints. You want to satisfy as many as possible, or you're given a loss function. You want to set the weights in your neural network to minimize your loss function, right? There are things like that. For those types of tasks, we do know a quantum algorithm that can sort of generically help with those sorts of tasks. It's called Grover's algorithm, discovered in 1996. So Grover's algorithm can sort of take any list of n possible solutions to some problem and find a good solution, if there is one, in only about the square root of n number of steps, where in each step you can check whether solutions are good or not, right? And the way it works is by sort of querying about all of the solutions in superposition. But even having done that, you still need like square root of n steps. This is my point, okay? And you should think of n, the number of possible solutions, as something truly enormous, right? So like you could easily have in a combinatorial problem, like 2 to the 1,000 power possible solutions, right? Now, what's the square root of 2 to the 1,000? Well, it's 2 to the 500, right? So that's a smaller number, but still quite enormous, right? That's the kind of speed up that Grover's algorithm can give you. And for many, many tasks in AI and machine learning, like that is, still almost 30 years later, that's still the most that we would know how to do, even with a perfectly functioning quantum computer. And now there's even a further difficulty, which is that to run a quantum computer at all and to actually run it at scale with like thousands or millions of qubits, we expect that you would need something called error correction, to get the qubits to work reliably. And error correction imposes an overhead. Okay, it might mean that you need like thousands of physical qubits to simulate just a single qubit of your algorithm, right? A single logical qubit, as we call it. And so then you're talking about millions of qubits. You're talking about sort of paying a constant factor overhead, which could be in the millions, right? Just to run your quantum computation at all. Okay. And now if we're talking about Shor's factoring algorithm, which gets an exponential speed up, right, then that exponential speed up can still win out over like a factor of a million, constant slowdown, right? Like if you're trying to factor a 2,000 bit number, as is currently used for like high security applications on the internet, like a 2048 bit Diffie-Hellman key, let's say, or RSA key, then we don't really know how to do that in any feasible amount of time, or at least no one who knows how to do it has said so in public, other than via Shor's algorithm, other than via building an error-corrected quantum computer. which, it might fill a whole building on the current estimates. It might take a week. Okay, but it would work. It would factor this 2048-bit number. With Grover's algorithm, if you're paying a factor of a million overhead, right, and the speed up you're getting is only square root, then, the crossover point where that starts outperforming what you could do with a classical computer, that gets pushed out even further into the future, right? And so then, in order for, the Grover speed up to be practical, which is really when I think quantum computers would really, start being very broadly useful for AI, then either you need like super enormous quantum computers, or else someone has to discover a better way of doing error correction with a lower overhead. Okay. So, but in the meantime, none of what I've just explained to you has stopped like hundreds of people from talking up, how quantum computers are going to revolutionize AI and machine learning in the past 10 or 15 years, and even raising, billions of dollars in venture capital based on this, hope or belief that they will, right? And people have used several strategies. I mean, one of them is to just ignore all the issues, right? Just sort of talk as if quantum computers will give exponential speed ups for all these AI problems, and just hope that no one knows enough to even, say, hey, wait a minute, right? Another strategy, though, is to there are heuristic quantum algorithms, that might get exponential speed ups for AI problems in some cases. At least, we don't really know if they will, but we can't rule out the possibility that they will, right? And so you can, just like with classical heuristics, like simulated annealing or, genetic algorithms, things like that, right? Typically, it's not a matter of proof, right? We can't prove what these algorithms do. We could just try them out and see that, often enough they do work, right? And, I mean, the entire deep learning revolution was based on, an approach where, we had no way to prove in advance that any of this was going to work, right? We just had to try it and see. Okay. So, there are quantum algorithms that are in the same category where, we don't yet have the scalable quantum computers on which to try them out, right? We can only try them on very small quantum computers, or of course we can simulate them using classical computers. Okay, but but then we're also very limited to small sizes, because that's the whole point of a quantum computer, right? That the cost of simulating it classically is can be enormous. Okay, so these are things like what's called the quantum adiabatic algorithm, which is like a quantum enhanced version of simulated annealing, proposed in 1999. More recent variants like this QAOA, quantum approximate optimization algorithm, and other things. And now, because we don't understand these algorithms, people are free to just make the most optimistic possible assumptions, right, about what they'll do, and present it to journalists or to investors, as if it's fact, right? So that's another thing people do. And then there's a kind of subtlety, right, which is that often with a quantum algorithm you can make it look like you've gotten the right answer, in a very short amount of time, in this incredibly impressive way. And the only problem is that you can't measure to see the answer. Okay. So often quantum algorithms can solve very hard problems in a sort of implicit way, where the answer is represented by the final quantum state, right? By this, this sort of mathematical object, this vector of complex numbers that we use to describe the output state. And so then, if you tell that to someone who doesn't really understand the subject, then they will think that a quantum computer has then solved this super hard problem super fast. An example would be like inverting a matrix, solving a system of linear equations in only logarithmic time, right? And then people say, oh, wow, you can do that. Well, then, of course, that's useful for AI, right? And this is, this is based on an algorithm called HHL, Haro Hasadim Lloyd that was discovered in 2008 or so, where it kind of looks like it's solving a linear system in only logarithmic time, exponentially faster than we could do classically. The trouble is that the solution is only represented as a quantum state. And now, in real life, you have to measure that state, right? And you only get a tiny, tiny little probabilistic sample about the output when you measure. Okay, so HHL, these algorithms like that might be an ingredient in some future quantum algorithm that would get an exponential speed up for something practical, right? But it would have to be one piece of a larger algorithm, right? Something that could actually make use of that quantum state that's produced as output. Okay, so this is I'm explaining to you some of the situation of what are the prospects for a quantum computer to revolutionize AI, right? And there's all these sort of possibilities that are all sort of blocked by something, right? Either blocked by the fact that Grover's algorithm seems like the best that we can do for these general search problems, or it's blocked by the fact that the output is a quantum state. Okay, or or it depends on these heuristic algorithms that we can't analyze, and maybe they'll give huge speed ups in practice, but we need a quantum computer before we can find out. So there was a clear claim to get like a quantum speed up for recommendation systems, for like the kind of thing that Netflix does, recommending movies to users, and that was proposed in 2016. And that and I really liked it because I could see that it got around all of these issues, and so I gave a student who was actually an 18-year-old undergrad at UT Austin by the name of Ewin Tang, right? I gave her the problem. Can you prove that this quantum speedup is for real? Which means prove that any classical algorithm that gives you the same information about like the user's preferences, prove that it would take exponentially longer than the quantum algorithm takes. And so my student Ewin spent a year on that problem, and then after a year, failed attempts came to me and said, "Listen, I think the reason I haven't been able to prove this is that it's not true. I think there is a classical algorithm that only gets, that's only polynomially slower than the quantum algorithm is." And I was skeptical, but I told her to pursue this, and it turned out to be right. Okay, so that was a breakthrough result like 5 years ago, which destroyed, one of the main examples that we had of how you might get an exponential quantum speed up for machine learning problems, and then building on Ewin's breakthrough, a whole bunch of other quantum machine learning algorithms have now been dequantized, or as I like to say, Ewinized, right? And so I still think that quantum machine learning is extremely interesting as a scientific subject, right? Like we ought to know, what are the limits here? If either can we figure out some killer app for quantum computers and machine learning problems, or if we can't, then why not? Is something that I equally want to know. And then of course there are lots of machine learning problems that themselves involve quantum mechanics, right? Where you're trying to learn properties of a quantum state or properties of a Hamiltonian, which is like the way that quantum states change over time. And for those kinds of problems, there it's a completely different story. There, yes, I'm very optimistic that quantum computers will help us a lot, right? And that and in any case, tools from quantum information will be the relevant ones for understanding those problems, right? And there's been a lot of progress there. Okay, so those are all things that and some of those are things that I've worked on personally. I've worked on procedures for learning properties of quantum states using like exponentially fewer measurements than a naive approach would need, right? Like if you want to learn, a full description of a quantum state, of like 100 qubits, there are 2 to the 100th power parameters that you have to learn, right? That's an absolutely enormous learning problem. Okay. But I had a paper in 2007 where I said, okay, but if we change the question a little, and we say, well, you just need to predict the outcomes of most measurements on the state for some, given some probability distribution over measurements that have yes or no outcomes, then the amount of data that you need to do that is exponentially smaller. It's only like, linear in 100, right? It's order of 100 data points that you need. Okay, so and the way that I was able to prove that was by using techniques from classical machine learning, right? From classical computational learning theory, and just combining those with quantum information theory. Okay, and since then I've done many other things, along the same line. One of them was called shadow tomography, like 5 years ago, which so I proposed a way that you could learn the outcomes of all measurements on your state that belong to some pre-decided list, even if that list is very enormous. So you can like learn the outcomes of exponentially many different measurements on a state with exponentially many parameters, given by carefully measuring only a polynomial number of copies of the state, right? And that again uses techniques from machine learning. So there are lots of points of intersection between quantum computing and machine learning. Whether or not quantum computers will be revolutionary for solving classical machine learning problems, which I regard as still very much an open question. But yeah, so then this year, I'm sort of on leave to work at OpenAI, and what I'm doing for OpenAI actually has nothing to do with quantum computing. So it does not draw on any of that intersection, right? It's and that's just because OpenAI approached me. Some people there, I guess, were reading my blog, and a year ago, someone was asking me in my comment section, like, Scott, what is it going to take to get you to stop wasting your life on all of this quantum stuff and work on the only problem that matters nowadays, which is preventing a super intelligent AI from taking over the world. And I said, well, so like I've been familiar with these arguments for a long time, right? I've known Eliezer Yudkowsky since like 2006 or so, right? The sort of AI doom people who have been very extremely worried about this particular scenario where AI becomes super intelligent and it takes over, and and they've basically felt that everyone else should drop what they're doing and just think about that. And I was always very skeptical of that, right? Partly because I felt like, well, even like supposing that I agreed that this was a big issue, and I would say, and who knows, right? Who knows how long it will take for AI to reach a human or a superhuman level? It could be hundreds or even thousands of years for all we know, right? But supposing that were to happen in the next 20 years or whatever, well, what do you want me to do about it, right? Like, I didn't see a research program there that had either math, like axioms that we all agree on and that we can prove theorems about, or experiments that we can do that sort of tell us something useful. It all seemed like armchair philosophizing, right? Seemed like just imagining a super powerful super intelligence that is almost godlike and that can do whatever it wants, and that almost anything that it might want would be unaligned with human values, and then very quickly it just kills all humans, like the Terminator or the Matrix or whatever, and it takes over the world. And and it was just a very depressing subject, because you just convince yourself over and over again that there is nothing you can do faced with such a super intelligence, and you just you refute 10,000 ideas for things that you could do by saying, okay, no, but the super intelligence will be too smart, and whatever strategy you have, it will have foreseen it, and it will have found a way around that. Okay. So it just didn't seem. I just never felt like there was that much meat. It didn't seem that, whereas like in quantum compute, so we don't have a super intelligent AI. We don't have a scalable quantum computer either, right? But the difference is that we can, with the quantum computer, at least we can do all of this interesting math, right? We know exactly, what the device should be, and we can start actually understanding what it will and won't be capable of. And then also, of course, there are the people who do experiments and who are trying to build the actual machines, right? Which seems like seem to me like actually an easy problem compared to replicating the human brain, compared to building an AI. Um, um, but then so the OpenAI people approached me like a year ago. Yeah. So because of this conversation that I was having on my blog, right? And what I was saying in that conversation was, what I would really need is kind of a meaty problem. Like, at least like now, like I could start to see, okay, AI is changing the world, right? There are now these artifacts like GPT, and DALL-E, which are, way beyond where I would have expected AI would have been by now, right? I didn't know that just taking neural networks and back propagation, taking ideas that were around, in the 80s, around when I was a student in the 90s, right, and just scaling them up, right, would produce such astounding results, right, because again, as I said before, there are no theorems that tell us any of this stuff, right? The only test of all these things, has been empirical, right? And I guess so I didn't predict these things. My only defense is that hardly anyone else predicted them either, right? Including AI experts, including even many of the ones who were most optimistic. They didn't know that this particular approach was going to get as far as it would, right? But it has. And and given that it's happened, the least that I can do is update on that, right? I don't want to be, I have colleagues in computer science who, look at what has happened in the past few years with GPT and other large language models. And for them, the main problem is to just invent reasons why none of it counts. Why none of this is true intelligence. None of it is that impressive or interesting. And no, it clearly is impressive, right? Regardless of how we talk about what is going on, inside of these deep nets, I think they're clearly going to change the world at least as much as the internet did, right? That is just kind of like a loose lower bound, right? At this point. And so of course, I was very excited about that, but I didn't really know, is there anything that a theoretical computer scientist like me, could contribute to this, right? Because it's not obvious. I mean, it's much harder to apply theory to AI than it is to apply theory to quantum computing or to cryptography or things like that, right? Because of the issue that we were talking about, because of the fact that AI works by exploiting these real world regularities that tend to be very hard to formalize. Okay, but then Ilya Sutskever, who's a co-founder of OpenAI, and Jan Leike, who's the head of the safety group at OpenAI, started talking to me a year ago and saying, "Look, we think that we do actually have problems where a theoretical perspective would be helpful." and we want you to take a year off from your quantum computing job and help us think about those problems. And I was kind of like, why do you want me? And they, I think part of it was that one of my former students in quantum computing named Paul Christiano, who was a real superstar student, absolutely amazing. We worked together on quantum money. Then he got a PhD at Berkeley with my same former advisor, Umesh Vazirani. And then Paul left quantum computing and became a full-time AI safety person because this was the most important thing. And Paul actually helped to start the safety group at OpenAI, and then left OpenAI to start his own AI safety organization called ARC, Alignment Research Center. Okay, but Paul helped to convince everyone in this community that actually computational complexity is one of the keys to AI alignment, right? And these things we know in particular about interactive proof systems, about how like a very weak verifier could nevertheless verify the behavior of a super powerful and untrustworthy prover, right? That these were going to be relevant to AI, at least at the level of analogy, and maybe even more than an analogy, right? So I think it was because of Paul's influence that they were interested in me at all. But then I said, well, look, I have. It sounds exciting, but I'm in Austin. You're in San Francisco. I've got kids. I've got obligations to my students, and they said, okay, you can work remotely. You can just work in Austin and just come visit us every month or so. And I said, well, that sounds great. Maybe I'll do it some other year when I can arrange it. And they said, trust us, this is going to be a really, really big year for AI, for large language models. You want to be involved this year. And I said, okay, let me see if I can rearrange my teaching schedule and do that. So that is how I ended up doing this year.
I do want to come back to some of your recent writings on things like the orthogonality thesis and stuff like that. But perhaps first, let's talk about what you were working on at OpenAI. And you've been doing a few AI related things recently. So I saw you had a very preliminary analysis of DALL-E 2 that you were on with Gary Marcus, for instance.
Oh, yeah, that was before I even started at OpenAI, and that was basically all that happened was that Gary Marcus and Ernie Davis, who were two professors at NYU, who've generally been very, very skeptical about generative AI. They wanted to test DALL-E's ability at compositionality. So like fulfilling complicated prompts, like a blue cube that is on top of a red sphere next to an orange cone, and so forth. You're right. And and like, not surprisingly, when you pile on too many constraints like that, then DALL-E starts messing it up, right? But they didn't have access to DALL-E at that point. So and I did, because I was just talking to OpenAI at that point, but they just gave me DALL-E access. And I helped them run the experiments for these prompts. And DALL-E actually did better than they were expecting it to, right? Not perfectly, but better than they had expected. And so then they wrote a paper about it, and they added me as a co-author. And that was all. But since since I've been at OpenAI, the easiest to explain of all the things that I've worked on there is a scheme for watermarking the outputs of
Yes.
GPT, right? So so I realized, like last summer, like I had this very, very aggressive and inventive troll on my blog who was, impersonating all these people, including friends of mine, right? Doing unfortunately, a really good job of it, right? And so that like even my other friends were fooled, right? And and then I got into this like kind of paranoid mindset where I could no longer trust anything that anyone was posting on my blog as being really from that person, right? And I had to institute some email verification system, and fine, but then I realized like, oh my god, GPT is going to automate all kinds of nefarious things, passing off text as not what it looks like, right? And so anyone who wants to impersonate people online, or who wants to engage in fraud or let's say spamming every comment section with pro Putin propaganda or whatever, or more prosaically, every student who wants to cheat on their term paper, right, is going to have this incredible tool with which to do that, right? And wouldn't it be great if we could find a way of distinguishing AI generated text from human generated text, right? Yeah, in order to clamp down on all of these categories of misuse. Okay, now in AI safety, like people are constantly talking about timelines and like, where do you think, the world is going to be in 10 years or 20 years? How will AI have changed things? Will there be existential risks and so on? Like, I can't see 10 or 20 years into the future. In this particular instance, I'm proud of myself that I at least saw like 3 months into the future, because what happened then is I started working on this problem and sort of banging the drum about it within OpenAI, and I came up with a scheme for watermarking the outputs of GPT. Okay, so what does that mean? It means that you would so the way that GPT works is is inherently probabilistic, right? It's taking as input like the sequence of previous words, or what are called tokens, which could also be like punctuation marks, parts of words and so forth. So it's taking a sequence of let's say up to a couple thousand tokens in your context window. It is putting them into this neural network, this giant transformer net. And then what the neural network outputs is a probability distribution over possibilities for the next token, right? So for each possible next word, let's say, it has some probability. Okay, now in some cases, almost all of the probability will be concentrated on a single choice. Okay, if I say the ball rolls down right, GPT knows that the next word is like more than 99% likely to be hill. Okay. In other cases, it will be balanced between multiple possibilities that might be kind of equally likely, right? And normally, what GPT does is that it just samples from that distribution. Okay, it just picks the net, right. Now you can run it in other modes. So there's a parameter called temperature. If you set the temperature to 0, what you're telling it to do is always pick the token with the highest probability. Right. So that makes it deterministic. Okay. But now the idea with watermarking is that there's a different thing that you can do, which is you can pick the next token pseudo randomly. Okay. So you can pick it in such a way that it looks it looks like it is chosen from the distribution that GPT wanted, right? Which means that to a normal user, the output will be indistinguishable from normal GPT output. Okay, right? It'll look just the same, but secretly you are, you're choosing the next token in a secretly deterministic way, and not only that, you're choosing it in order to systematically bias a certain score that can be calculated later, like as a function of just the words in the GPT output, right? So now if you use GPT to generate, to write your term paper for you, right? And let's say, then your professor is suspicious, so they take the term paper, they feed it into a detection tool, which OpenAI would also provide, right? And then that detection tool looks at the words. It knows the key to the pseudo random function. The same one that was used for picking the words, and then it calculates a sum, over all sequences of, let's say 5 or so consecutive words, and it sees that sum, that score, is anomalously large, right? And then it knows that, like let's say for a text with reasonable, that's reasonably long, it knows with 99.9% probability or something that the GPT must have generated this, right? This score would not be so large just by chance. So, um, anyway, so I came up with this. It was I worked with an engineer at OpenAI named Hendrik Kirchner, who implemented this idea, and we tried it out, and then in December, OpenAI released ChatGPT, right, which blew up, became viral in a way, way beyond what OpenAI was expecting, right? And because it was not a huge advance on the models that had preceded it, but it was freely available and it had a nice user interface, right? And and that was all it took to get like the fastest adoption of any service in the history of the internet, literally. Okay, something on the order of 100 million people signed up for it, in a matter of like a couple months. Okay, and then it took only that. It took, like within a month or so, students were in fact using it to cheat on their term papers, as some of us had foreseen, as we had worried about, right? And we started getting just direct pleas from professors, like, it will OpenAI have a solution to this? Like, please hurry up. Okay. And now there are other solutions that people have come up with. So there was an undergrad at Princeton by the name of Edward Tien, who built something called GPT Zero, which is just a detection tool. I mean, all it is like you treat distinguishing AI text from human text as yet another AI problem, right? So you just train another AI model at that discrimination task. Okay, we at OpenAI released our own version of the same thing called Detect GPT. Okay, a little bit later. Okay, and these tools, I mean, they are better than chance. They're better than nothing. But the trouble is, like, they can falsely accuse, a student of, of AI assisted plagiarism, right? They are nowhere close to 100% accurate, or even 99%, right? They and if you want to use it to, like, for unmasking, the use of GPT, there were just too many false positives. That is the central thing where I think watermarking would be better than these discriminator models in pushing the rate of false positives almost to zero. Okay. Now, in order to do watermarking, you have to change slightly the way that the GPT itself operates, right? And then that will create a watermark, and which will then only work for GPT, right? If someone else, trains their own language model, right, that might not have the watermark, right? And so then, now it becomes a very hard question. Like, you could say, if someone wants to be responsible and watermark their language model, are they then putting themselves at a competitive disadvantage? right? Will will people just switch to a competitor's model? If they want to, not have everything they write be everything they have their AI write be watermarked in that way. So that's one issue. Now, I should. OpenAI has not yet deployed my watermarking scheme. I am hopeful that watermarking will be part of the solution going forward. It can't be the only solution to these problems, right? For a number of reasons. One of which is that anyone who is clever enough can find ways to defeat watermarking, or probably defeat almost any other method, right? That we could think of.
It's a cat and mouse game.
Yeah, it is a cat and mouse game ultimately. I mean, even someone who just asks GPT to write their term paper in French and then puts it into Google Translate, and then like fixes the errors. Okay, that would be a little bit more effort, maybe, but that I don't know how to watermark text in a way that would survive translation from one language to another one, right? And there are other attacks that one can think of. Okay, but we can at least make it a little bit more expensive for people to use GPT in these ways, and we can at least get started, right? Sometimes in a cat and mouse game, there's nothing to do except just try to be the best cat you can be, right? Google, I think, never discovered a principled solution to the people trying to game search engine results, all the SEO people, right? But they just try to stay one step ahead of them. And I could easily foresee the same thing happening with, people who are using language models to generate for academic cheating, or for propaganda, or for fraud, or for all of these different things. So yeah, so that's some of what I've been thinking about at OpenAI, and then I have other more speculative, more theoretical projects, but it's been very amusing for me that like I would have weekly calls with Ilya Sutskever, right? And he's an extremely interesting and thoughtful guy. Okay, but I would tell him about progress on watermarking, and he would say, okay, yeah, that's great, Scott, you should keep thinking about that, but what we really want to know is kind of how can you use computational complexity theory to define what it means for the AI to love humanity, and how can you define the concept of goodness in formal mathematical terms. And I'm like, I'll keep thinking about that. Yeah, those are tough questions, right? Harder to make progress on, right? But now, of course, the reason why I decided to get involved in this year is that now, like, there are meaty problems that you can make clear progress on, right? Like, I don't feel like I have solved the watermarking problem, but I feel like I at least made an advance on it, right? And I think one could work just on that watermarking problem for 10 more years, and there would still be more to say about it, right? And I feel like we're just in the very early days now of AI safety, AI alignment as a technical field that you can make actual legible progress in.
Some of those, as it were, bigger questions that Ilya Sutskever posed to you about how can you use computational complexity to measure these things that seem fundamentally human is really interesting because, of course, there's a number of people who will reject out of hand that you can mathematically define certain aspects of humanity. Somebody who I know, Joel Lehman, recently put out a really interesting paper that he titled Machine Love, in which he was exploring whether large language models could embody, I think in this case, concepts of love that were derived from A, Maslow's hierarchy of needs, and then B, Eric Fromm's concept of active love. And so that seemed like a really interesting direction. And of course, he notes a set of limitations, but I am curious just in some of those wild questions that you've been getting from Ilya, how you've started to think about them.
Um, yeah, I have not succeeded in sort of defining what it means for AI to love humanity, right? I mean, I think there actually there are some interesting ideas that the AI alignment community has come up with about how do you formalize these concepts. I mean, one that I like is something called coherent extrapolated volition, right? Where you basically what it basically means is you say, you don't want to train your AI on current human values, because, like, oh my god, what if we trained an AI on the human values of the year 1800, right, and it were to lock those in forever? Like, that would be terrible, right? People believe terrible things in the year 1800, or at least things that we now regard, almost universally regard as having been terrible, right? And surely today, we also have values that our descendants, if we have descendants, will look back on with horror, right? We might be able to guess at what some of those are. We don't know for certain, right? But what in some sense, the values that we want, the AI to have, are like the values that we would have if we had 10,000 years to sit and think about it. If we could just sit in this, like the philosophers in Athens with our togas, for like thousands of years, and just debate and refine our moral intuitions, right? Whatever views we would eventually come to. Okay, but now that might already be enough for the AI to go on, right? You might be able to just tell an AI that, just simulate, humans having this moral discussion for, this, enormous amount of time, which, thousands of years might not actually be that much if you're an AI, to simulate, and then implement whatever values, the humans would agree on, after that much reflection. Okay, so there are ideas like that. Now it's very hard, but what's very hard is to say anything mathematical and non-trivial about any of these proposals, right? So I don't know that I've made much progress there. I mean, one question that where I feel like maybe I did have something a little bit interesting, was the question of an off switch. Okay, so you could say, the an off switch is like the first AI alignment idea in the world, right? It's the first and most basic of, either switching it off when it starts to go berserk, or pulling the plug, or whatever, right? And the alignment people have, for a long time, had arguments that is not good enough, right? And why isn't it good enough? Well, because, if the AI is intelligent enough, then, it will have foreseen that the humans, might turn it off, and it will probably have goals that would best be served if it's not switched off, right? Whatever its goals are, if, it can best pursue those goals if it's still on. And so, it will, may have come up with a plan, either disabling its off switch, or talking the humans out of turning it off, or making copies of itself all over the internet, or and so there's a whole subfield of AI safety called corrigibility, right? That's about, like, how can you change the AI's objective later if you decide it wasn't the right one, or, as one special case, how can you switch it off? Uh, and what I realized, is, there's been, a recent really exciting work in at the intersection of cryptography and machine learning, which has shown, at least in some cases, how to insert a cryptographic backdoor into a machine learning model. Okay, so there was a paper by Shafi Goldwasser and Vinod Vaikuntanathan, and two others. These are cryptographers. Some of them are actually my former colleagues at MIT, but they, at least for like certain depth 2 neural networks. They show that you can insert a backdoor where, like, if the network gets this certain, like, bizarre input, then it does some special thing that you want it to do, such as, switching itself off or whatever. Okay. But now, even if you could see all of the weights of the neural net, it would be computationally intractable for you to find that secret input if you weren't told it, right? Like, you would have to solve a hard cryptographic problem. In that case, it's something called the planted clique problem. Like, given a large graph that looks kind of random, find some anomalously large set of vertices that are all connected to one another. Okay, that's what is known in theoretical computer science as the planted clique problem. Um, and so that, they could show that finding the back door is at least as hard as solving that. Okay, and now they viewed that as mostly a negative for AI safety. Like, a bad person could insert this back door into a machine learning model that people would then use, and that bad, and no one would be able to detect it, and then that bad person could go and trigger the back door whenever they wanted to, right? But, like many things, in science, it's like, have this property of, like, if the world gives you a lemon, you can make lemonade. Right. Right. Whether something is good or bad all depends on who is doing it. Right. And so this could also be seen as a positive for AI alignment. Right. Like, what if we use these backdoors to insert a cryptographic off switch into a powerful AI model? Okay. So you could have like a robot where, like only humans know, this secret instruction, that will cause the robot to shut down or something. And, even if the robot knows its own weights and can modify them, it would not easily find that shutdown instruction. Right. So that's an idea that I've been playing with. I mean, I think that we're really at the beginning of this thing that, I could easily imagine this being a large part of the whole future of cryptography. This, like, how do you, what kind of cryptographic stuff can you insert into a machine learning model? Or how hard is it to detect that stuff once inserted? I've taken to calling this neurocryptography. Uh, someone else suggested calling it deep crypto, but I'm not sure that I think we have to veto that name. Uh, so that is something I've been thinking about. And in some sense, like, I think it's possible to make progress here, just because this is you don't really have to understand what's going on inside the AI that well, right? You can just take the AI as given and then put this cryptographic thing on top of it. Okay. Now, these sort of AI alignment purists, they tend to be very skeptical that anything along those lines could possibly work, right? But I think, at least in the near term, these things might help. They might give us more time, and we can make progress on them. And we can worry about, the next thing when we get to it, right? And that is kind of what we do in science, right? We don't even imagine that we can predict what the world is going to be, in 20 years, but we can at least try to, fix the problems of the world of 1 year from now, right? And leave it to the people of a year from now to fix the problems of 2 years from now, and so forth.
So, as a last question, I suppose this could be maybe a summary of many things that you just said now and written on your blog. I find your stance, I suppose, as a reform AI alignment person rather interesting. And I think it's interesting that we're talking about this now in the light of Eliezer Yudkowsky's recent comments. You've written quite a bit about what he said, but I think some of his recent writing, people have taken his Time article to be saying, well, you shouldn't be afraid to do airstrikes on data centers. I think a lot of people are kind of up in arms and have very different reactions to what he said. And as a closing out point, I guess I'd just love for you to respond to some of the discourse that's gone on in and around the way that people are reacting to GPT-4, to how Eliezer is thinking about it.
Yeah. Well, I mean, I think that if you take, Eliezer's starting assumptions, right, that like at any point, AI could just go off a cliff, become super intelligent, right? At that point, we should expect that first of all, this orthogonality thesis, which says that an arbitrarily smart AI could have, from our standpoint, arbitrarily stupid goals, like converting the whole universe into paper clips or things like that. And second of all, this instrumental convergence, which says that no matter what the AI's goals, like as a first step, it's probably going to want to amass as much power and resources as possible to help it achieve its goals, right? And we also believe in this possibility, in the likelihood, I should say, of deceptive alignment, an AI that will pretend to be, doing all the things we want and following our instructions, but is actually just biding its time until, the moment to strike, right, against humanity. And at that moment, maybe we'll just all drop dead from some, engineered toxin, at the same second, or something like that. And we'll never have seen it coming, right? If you accept all of those assumptions, then I think that like yes, you do logically end up at the place where he now is, right? Which is saying just shut it all down. It is more important than preventing a nuclear war, right? And have an international agreement to prevent any further scaling of AI, enforced, as he explicitly said, via airstrikes, or the threat of airstrikes against, anyone who didn't cooperate. Um, Now I think, um, I am not at that point, right? I mean, I sort of, I get off the train in several places, right? But one of them is, I think that, even if one person, believes that, like, there is not evidence of that now that sort of it can be made legible to the whole world, right? Like, right now, I think, the death toll from GPT, I want to say that it stands at zero. Uh, it might, there is, within the past couple of weeks, there was unfortunately a man in Belgium who committed suicide after spending a lot of time interacting with a language model. Right now, the causation is hard to tease out. He obviously had, was depressed beforehand, had some, conditions, but let's say, the out of hundreds of, millions of people who have used these things now, the death toll is either zero or one, right? And so I think that if and when a language model is used by terrorists, let's say, to launch to help them design a terrorist attack, to help them design a new weapon, a new engineered pandemic, or something like that, and it causes mass suffering, I think at that point the whole conversation will be different. And there will then be, all the governments will be, passing legislation to try to control this, restrict this, slow it down. um, and the companies themselves will want to slow it down. I mean, they may want to make money, but they also don't want to be killing people and destroying the world, right? So this is now, the issue is that we're not at that point. Some people think it's inevitable that it's going to get there. Other people don't think so, right? And there is a one hypothesis that says, well, like, these language models, as impressive as they are, they're kind of ultimately bottlenecked by just how intelligent, how much intelligence was there in their training data, right? There's like, like they're never going to be more intelligent than like the best experts that they can find on the internet in order to train themselves on, right? And I think to the extent that people believe that thesis, then maybe this never becomes that dangerous, right? So what I have found the hardest to wrap my head around here are the people who, on the one hand, they want to dismiss language models as stochastic parrots, as glorified autocomplete, as just not very impressive, not interesting. They don't truly understand the world. They don't really understand semantics, or they don't have they're a symbol grounding or anything like that. But then on the other hand, they also think the language models are terrifying and it has to be shut down. Right? That combination seems like very hard to make consistent. It's like you can make it consistent, you can reconcile those two views, but you seem to have to do something like saying, okay, the reason that language models are dangerous is that most people are idiots, right? Like I can easily see that this is unimpressive in a stochastic parrot, but all the simpletons, all the plebeians, they will all be tricked by this, right? Into and it will ruin their lives or somehow, right? So I think for the people who think that the language models are not impressive or not intelligent, I think that they are inadvertently making an argument that there's no reason to stop scaling. Scaling should scaling this should actually be fine, right? We'll see that the things run into a limit, as the skeptics predicted, and we'll learn something from that, and and that will be that, right? I think that to really have an intellectually consistent case for stopping the scaling, the consistent case that I see is the existential risk case. Right. It is, it is the, sort of vaguely Yudkowskian case, right? That this could, make a sudden sharp turn to causing this catastrophe for the world. But again, for that, like I am, what I'm skeptical of is the scenario where everything seems fine and then instantly we all drop dead. Right. I think, that like if we've learned anything from this generation of AI, right, it's that it undergoes a learning process as humans undergo a learning process, right? Not identical to our learning process, but, like before it's amazing at math, it is mediocre at math. Before it's amazing at poetry, it is mediocre at poetry. Right. And I think before it is amazing at deceiving humans and taking over the world, it would first be mediocre at those things. Right. It would try to deceive people and not do very well. Or it would be able to help bad humans, take power, in some limited way, kill some limited number of people, as opposed to destroying the entire world. And so I feel like we might as well worry about those risks first.
I think that a lot of the writing you've done on this subject definitely is really articulate. And this was a good summary. Well, thank you so much for taking the time to chat with me today. This was really interesting.
Of course. Yeah, thank you for having me.
And that is a wrap, my friends. As I mentioned at the start of the episode, you can subscribe to The Gradient on Substack to receive not just this podcast, but also our articles and newsletters directly to your email. You can also visit us at thegradient.pub, where you'll find all of that, as well as more information about The Gradient and how you could even contribute if you're interested. And finally, if you enjoyed this episode, we would really appreciate your feedback. If you'd like to leave a comment or review, we'd love to know how we can make this series more interesting and informative to you. And with all that, I'll leave you until the next episode.